This is called Archimedes' problem. A spherical cap, that's the top portion of a sphere. So let's imagine, I don't know, that you filled up some sort of plastic sphere with water up to that point. Well, you've got a radius, the middle to every point, and then you've got sort of the height from the very top down here, we'll call that h, and this r, has volume v equals pi h squared, parentheses r minus 1/3 h squared, and a surface area, this is just the cap piece, the surface area of that is s equals 2 pi rh. What height h encloses the largest volume of a fixed surface area s? So let's imagine that this is a bubble forming on the ground and the surface of the bubble is fixed. Well, what's the largest volume of air that could be inside that bubble? And the problem will come up with an answer for h, but then we'll also make a sort of an interesting observation about what that h is later. So I need to solve this for a particular variable. Note r only shows up once, so maybe I'll take this and say s over 2 pi h to the negative 1 equals r, right? So then I'm going to substitute that in for v into the equation of v for r. So s 2 pi h to the negative 1. Notice I could write 1 over h, but I need to take the derivative. So h to the negative 1 is probably easier. 1/3 h. I'm going to distribute rather than worry about a product rule in the derivative. Oops. I say I'm going to do that. I better do it. Let's see. A pi times s over 2 pi. The pi's cancel, so I get s over 2. H squared times h to the negative 1 is h minus pi times 1/3 is pi thirds, h to the third. So this is a cubic. V prime becomes s over 2 minus, let's see, pi thirds times 3 h squared is just pi h squared. So this is my second derivative. If I'm trying to figure out where that equals 0, let's see, that equals 0. So s over 2 minus pi h squared equals 0. When s over 2 equals pi h squared, that is h squared equals s over 2 pi, or h. Remember, h is going to be not a negative number, so I can just write it as the square root of the surface area over 2 pi. Okay, now how do you know that is the largest volume? Well, you could take the second derivative here. Second derivative test seems pretty easy here. A derivative of a constant is 0 minus 2 pi h. For all positive values of h, for h greater than 0, this is negative. So the second derivative is negative. That means at this critical point, it's concave down, and that's a max. Okay, well, that's technically the end of this problem, but if you were trying to see sort of what does that actually say about the bubble or this maximal surface area, let's ask just a slightly more in-depth question. What does that tell you about r? How far is h not as a proportion of the surface area, which we have here, but as a proportion of r? So let's see. If I then put this into that equation, you can sort of see that I have s over 2 pi times h inverse. So h inverse is the reciprocal of that. Can you see how the reciprocal of that is the square root of 2 pi over s? Well, this is interesting. We have s over 2 pi to the 1, s over 2 pi to the negative 1/2, essentially. So what's that come out to? It says r, in this case, is the square root of s over 2 pi. Well, that's interesting. In other words, the height that maximizes the volume is what we call the hemisphere. It's when the height is equal to the radius, and you have exactly half of a sphere. And that's why so often when you see bubbles on the ground, they look exactly like half a sphere.